The story of an incredible scientific mystery, one that comes with a reward of 8 crore rupees for whoever can solve it. But this isn't just about money, it's an opportunity to uncover the deepest secrets of the universe. Can you imagine a puzzle that has baffled scientists for decades, and if solved, could completely change our understanding of reality? This is the unsolved enigma of quantum gravity. Imagine standing at the edge of a massive black hole, where time slows down, light gets trapped, and the laws of physics seem to break down. Or travel back 13.8 billion years to the very moment when the universe was born from an infinitely dense point. These are the places where Einstein's general theory of relativity and quantum mechanics clash. Two great theories, one for the vast cosmos, the other for the tiniest particles. But when we try to unify them, science's mathematics fails. The Clay Mathematics Institute has identified 7 great mathematical puzzles under its Millennium Prize problems, one of which is the Yang-Mills and mass gap problem, closely linked to quantum field theory. Anyone who finds a solution will be awarded $1 million, tilde 8 crore. Now, imagine if you had the chance to solve this mystery. Would you accept the challenge? Could you be the scientist who unravels this riddle and becomes immortal in the pages of history? This story is not just about science. It's about our very existence. Will we ever truly understand what gravity is? Could quantum gravity give us the theory of everything, a single framework to explain the entire universe? And if so, it would mean mastering time, space, matter, and energy. This is a race to unlock the universe's greatest mystery. And perhaps, the next great scientist could be you. So, are you ready to take on this puzzle? If this enigma is ever solved, we could finally understand the true nature of time, space, matter, and energy. It might even reveal the secrets of time travel, wormholes, and the multiverse. So, are you ready to embark on this thrilling journey with us? Will you take up the challenge to solve the greatest puzzle in science? Join us as we dive deep into this mysterious scientific adventure and explore it in detail, but in the simplest way possible. Rocket. Imagine you have a magical sheet. You hold it tightly from all 4 corners and stretch it. Now, if you place a small ball, like a table tennis ball, on this sheet, it will remain stable. But if you place a heavier ball, like a basketball, the sheet will bend downward. Now, if you gently push the small ball, it will start orbiting around the larger ball, just like planets orbit around the sun. This is the fundamental idea behind Einstein's general theory of relativity. To understand what is happening here, we can visualize the large ball as the sun, the small ball as the Earth, and the stretched elastic sheet as spacetime. This means that massive objects, like the sun, planets, and black holes, warp spacetime, creating gravity. This very principle explains why the moon orbits the Earth, and why the Earth orbits the sun. It is a depiction of gravity that helps us understand how things work in the universe. But when we dive into the smallest scale of the universe, the quantum world, the laws of relativity break down. The attempt to unify quantum mechanics and general relativity has led to theories like quantum gravity, but so far, it remains an unsolved mystery. To fully understand phenomena like black holes and the Big Bang, we need a theory that can unify both of these branches of physics. Scientists are exploring various approaches, such as string theory, loop quantum gravity, and the holographic principle, but no definitive answer has been found yet. However, this question is not just limited to scientific curiosity. If we can understand gravity at a quantum level, it could have a profound impact on our entire existence. We might discover new sources of energy, revolutionize space travel, and gain an entirely new perspective on the nature of time and reality. This mystery remains one of the most challenging puzzles in science, and perhaps, future advancements in technology and physics will help us uncover its secrets. Will you be the one to solve this puzzle? Perhaps the next Nobel Prize is waiting for you. What does the general theory of relativity say? Einstein's general theory of relativity states 2 key ideas. Asterisk space and time are not separate but part of the same continuum, called spacetime. Asterisk gravity is not an actual force, but rather the bending of spacetime. The heavier an object is, the more it bends spacetime. Black holes, the deepest pits in spacetime. A black hole is so massive that it bends spacetime to such an extent that nothing, not even light, can escape its pull. You can imagine it as an extremely deep well, where anything that falls in can never come back out. And if you go near a black hole, time will slow down for you. GPS satellites and time travel also operate under the same principle. Have you ever wondered how GPS, Google Maps, in our mobile phones works so accurately? Behind this lies Einstein's theory of relativity. GPS satellites orbit high above the Earth. Since gravity is weaker there, their time runs slightly faster compared to time on Earth. If this correction were not made, GPS would accumulate an error of up to 10 kilometers per day. Scientists use Einstein's theory to correct this. Moving at high speeds slows down time. Twin paradox. Imagine Arav and his twin brother Kabir. Arav boards a rocket and travels close to the speed of light, while Kabir stays on Earth. When Arav returns to Earth, he finds that Kabir has aged significantly, but he himself remains young. This happens because moving at high speeds slows down time. This is called time dilation. That is why, if someone travels at the speed of light, they can actually move into the future. How can sunlight bend? Gravitational lensing. When light passes near a very massive object, such as a black hole or a galaxy, it bends. This phenomenon is called gravitational lensing. Using this technique, scientists can observe galaxies that are extremely far away. Einstein proved this in 1919, when the position of stars appeared to shift due to the bending of light around the sun. If this theory didn't exist, GPS would never be able to provide accurate time. We wouldn't know anything about black holes. We wouldn't understand how planets orbit the sun. The mysteries of time and space in the universe would remain unsolved. Einstein's theory is one of the greatest achievements of science. Gravity is not a force but rather a curvature of spacetime. Massive objects bend spacetime, creating gravity. Moving at high speeds slows down time. Black holes bend spacetime so much that even light cannot escape. Einstein's theory is used in GPS and satellites. This theory is the key to understanding the universe. A mysterious world where nothing is certain. One day, a boy named Arav went to his grandfather and asked, "Grandfather, if I throw a ball into the air, where will it fall?" His grandfather smiled and said, "Son, the ball will fall exactly where it should. But if this were the quantum world, it could fall in multiple places at once." Arav was shocked. How is that possible? This is what quantum mechanics is, said his grandfather. Quantum mechanics is the branch of science that attempts to understand the behavior of extremely small particles, atoms, electrons, photons. It reveals that the tiny particles that make up the universe behave very differently from the rules we observe in our everyday world. Here, things can exist in two places at the same time, change without being touched, and sometimes disappear altogether. To put it simply, just like a cat is either alive or dead, in the quantum world, it can be both alive and dead at the same time. Superposition is when one thing can exist in multiple places at the same time. Rocket. Imagine a mysterious world. One day, a boy named Arav was walking in the garden with his grandfather. Suddenly, he stopped and said, "Grandfather, if I am standing here, I cannot be somewhere else at the same time, right?" His grandfather laughed and said, "That's right, my son. In our world, that's not possible. But if you were in the quantum world, you could exist in multiple places at the same time." Arav was shocked and said, "How is that possible?" His grandfather smiled and said, "That is the magic of superposition." Superposition is a principle of quantum mechanics, which states that a particle can exist in multiple places at the same time, but only until we measure it. As soon as we try to observe it, it appears in a single place. Let's understand this with a simple example. When you are in a room, you are either near the door or by the window. But in the quantum world, you could be at the door and the window at the same time. If you had the chance, how fast would you like to travel? Do you believe that humans will be able to time travel in the future? Atom symbol. What is an electron? Or the electrical particle of the universe. High voltage sign. The electron is a crucial particle of the universe, without which modern life would be impossible. Imagine if one day your mobile phone couldn't charge, or if turning on a light bulb didn't produce any light. None of this would be possible without electrons. Electrons are the particles that generate electricity, and they are among the smallest and most fundamental particles in the universe. They are a part of the atom and carry a negative charge. Electrons orbit around the nucleus of the atom, just like planets revolve around the sun. In atomic structure, the proton carries a positive charge, the neutron has no charge, and the electron carries a negative charge. Electrons are the particles responsible for electricity, magnetism, and modern technology. In 1897, J.J. Thomson discovered the electron. He used the cathode ray tube experiment to find it, proving that atoms contain even smaller particles. Before this discovery, scientists believed that atoms were solid spheres, but the discovery of electrons changed that perception. Electrons never remain still. They are always in motion, orbiting around the atomic nucleus at speeds close to the speed of light. When electrons flow through a wire, we get electricity, which powers our mobile phones, TVs, light bulbs, computers, and almost every electronic device. When you turn on a switch, electrons start flowing through the wires, creating an electric current, and the light bulb turns on. The behavior of an electron is different from that of normal particles. Sometimes it behaves like a particle and sometimes like a wave. The double-slit experiment has already proven that an electron can exist in multiple places at once, and when it is not being observed, it exists in multiple locations. However, as soon as an attempt is made to observe it, it appears in only one place. Electrons create a magnetic field while spinning, and they are the primary force behind magnets. Devices like hard drives and microwaves operate based on the magnetic properties of electrons. In the quantum world, electrons are highly mysterious. Scientists have observed that electrons sometimes disappear without any apparent reason and reappear elsewhere. This process is called quantum tunneling, and it is the same process that keeps our sun burning. Without electrons, atoms would not exist, and without atoms, elements would not exist. Without elements, there would be no planets, stars, or life as we know it. In other words, without electrons, this entire universe would be impossible. Electrons are the universe's smallest superheroes. They are an essential part of the atom, responsible for electricity and magnetism. They are never stationary and are always in motion. They sometimes behave like particles and sometimes like waves, and without them, nothing in the universe would be possible. Now think, what would your life be like without electrons? Do you believe that in the future, humans will be able to harness the energy of electrons even more efficiently? The double-slit experiment is the most astonishing experiment in quantum mechanics, proving that electrons or any small particles sometimes behave like particles and sometimes like waves. If you are not observing them, they can pass through multiple paths at once, but as soon as you try to observe them, they pass through only a single path. This means that reality depends on whether you are observing it or not. One day, a boy named Arav asked his grandfather, "Grandfather, can something exist in multiple places at the same time?" His grandfather smiled and said, "Not in the ordinary world, but in the quantum world, it is entirely possible." Then, he explained to Arav one of science's most mysterious experiments, the double-slit experiment. Scientists took a metal plate and made two small slits in it. Behind this plate, they placed a screen where the impact marks of particles would appear. Then, They used an electron gun to shoot electrons one by one so that they would pass through the slits and hit the screen. At this point, two possibilities could occur. If the electrons behaved like particles, two straight lines would appear on the screen, right behind the slits. If the electrons behaved like waves, multiple deep and light wave-like patterns would appear on the screen. When no one observed the electrons, the screen showed a wave-like pattern instead of a particle-like pattern. This meant that the electrons passed through both slits simultaneously and interfered with themselves like waves. In other words, electrons can take multiple paths at once. They exist in a state of superposition. But when scientists placed a detector near the slits to observe which slit the electron passed through, the superposition collapsed. The electron chose only one slit to pass through. Now, the screen displayed only two straight lines, meaning the electrons started behaving like particles again. This experiment revealed three major conclusions. First, electrons can exist in multiple places at once, which is called turbulence is a very common natural phenomenon and can be seen in many places. When an airplane suddenly shakes during flight, it is due to air turbulence. It is also found in storms and cyclones. When a river's water crashes against rocks, its flow becomes disordered, and massive turbulence occurs during ocean storms. When fire burns, its flames and rising smoke behave erratically. This too is turbulence. Jupiter's massive storm, the Great Red Spot, exhibits turbulence. When astronomers observe stars through a telescope, their images flicker due to atmospheric turbulence on Earth. The Navier-Stokes equations are used to understand turbulence. These equations describe how a fluid or gas moves over time. However, when turbulence occurs, these equations become so complex that solving them is nearly impossible. Even today, scientists are searching for a complete solution to these equations, and whoever solves them will receive the Millennium Prize, worth approximately 8 crore rupees. To some extent, turbulence can be controlled. In air travel, pilots use advanced computer models and satellite data to predict turbulence. In cars and airplanes, aerodynamic designs are modified to reduce turbulence. Scientists take turbulence into account while designing rockets to ensure stability during launch. However, completely eliminating turbulence is impossible. Turbulence is present everywhere in nature, in air, water, fire, gas, and even in space. It is extremely difficult to solve mathematically. It remains an unsolved problem for scientists, and anyone who manages to solve it could receive an honor as prestigious as the Nobel Prize. Quantum gravity is a branch of physics that attempts to fit gravity into the laws of quantum mechanics. It is one of the most complex and unsolved problems in science. To understand why quantum gravity is important, we first need to understand what quantum mechanics and general relativity are and how they contradict each other. Quantum mechanics describes the rules that apply to atoms and even smaller particles. It explains that particles can exist in multiple states at the same time, superposition, and until we measure them, they behave like probability waves. It operates on a very microscopic scale. Einstein's general relativity states that gravity is the curvature of spacetime caused by any massive object. It operates on a very large scale: planets, stars, black holes, galaxies. General relativity is entirely based on continuous laws, whereas quantum physics follows completely probabilistic rules. Now, the problem arises when we try to understand phenomena like black holes or the Big Bang, as we need both quantum mechanics and gravity, but they do not align with each other. Why is quantum gravity necessary? We need a quantum theory of gravity to understand events like black holes, the Big Bang, and the origin of the universe. Black holes: when a star dies and forms a black hole, its gravitational force becomes so intense that classical physics laws fail. Big Bang: at the birth of the universe, it began from an infinitely dense point where quantum effects were significant. But we also need to understand gravity. Quantum structure of spacetime: if gravity itself is a quantum effect, it means that space and time, spacetime, would also be uncertain at the quantum level. Major theories explaining quantum gravity. Until now, no single theory has fully solved quantum gravity, but scientists have proposed several potential theories. Asterisk string theory. It states that all fundamental particles are actually tiny vibrating strings. It tries to define gravity as a quantum force. This theory includes 11 dimensions, but no direct evidence has been found yet. Asterisk loop quantum gravity. It suggests that space and time, spacetime, are made up of tiny quantum loops. This theory considers spacetime to be uncertain at the quantum level. It could help in understanding the structure of black holes and the Big Bang. Asterisk holographic principle. This theory suggests that information about a three-dimensional universe can be encoded on a two-dimensional surface. The study of black holes has led to the idea that gravity might be a kind of hologram. Asterisk twistor theory, proposed by the great physicist Roger Penrose. It suggests that spacetime and quantum mechanics can be connected through special mathematical structures called twistors. Will we ever find the answer to quantum gravity? So far, no experiment or observation has directly proven quantum gravity, but scientists are exploring several ways to test it. Studying the event horizon of black holes, quantum effects could be highly significant at the edge of a black hole. Analyzing gravitational waves, quantum effects might influence gravitational waves. CERN's Large Hadron Collider, LHC. This could help detect new particles and gravitational effects at extremely high energies. Why is quantum gravity important? Quantum gravity attempts to fit gravity into the laws of quantum mechanics. It could help solve deep mysteries like black holes, the Big Bang, and the beginning of the universe. Scientists have proposed several possible solutions, including string theory, loop quantum gravity, and the holographic principle, but none of these theories have been fully proven yet. Future advanced experiments and mathematical modeling could help us find the answer to this profound question. Will quantum gravity be the ultimate theory of the universe? This is an exciting question. If we fully understand quantum gravity, we may finally reach the theory of everything, a theory that unifies all forces and laws of the universe. So, what is the hardest problem in physics? Combining quantum mechanics plus general relativity is considered the most difficult task. If we ever understand quantum gravity, we could unlock the deepest mysteries of the universe. Do you think humans will be able to solve these puzzles in the future? Share your thoughts. Microscope: the mysterious world of science. The story of force atom symbol. Once upon a time, in a small village, there lived a curious boy named Arav. He was always eager to understand how things worked. One day, he went to his grandfather and asked, "Grandfather, why do things fall? When I throw a ball into the air, why does it come back down?" His grandfather smiled and said, "Son, it's all because of force." "Force? What is that?" Arav asked eagerly. His grandfather took him to the garden and picked up a ball. He dropped it on the ground and said, "Look, the ball falls down because of gravitational force." "What is gravitational force?" Arav asked. His grandfather explained, "Gravitational force is the power that pulls everything toward the earth. That's why we can stand on the ground and don't float in space." Asterisk: when we drop something from a building, it falls straight down. This happens due to gravity. Asterisk: the moon orbits around the earth because Earth's gravity pulls it. Grandfather threw the ball high into the air and said, "But son, gravity is not the only force. There are many types of forces in the world. The force that is applied by touching an object is called contact force." Asterisk: when Arav kicked the ball, it moved forward. This was the applied force from his foot. Asterisk: when he was riding his bicycle and applied the brakes, the cycle stopped. This was frictional force. Asterisk: pushing a chair with your hands makes it move forward. Asterisk: friction helps hold a pencil while writing. Position. Until someone observes them, electrons can pass through both slits simultaneously. This is the strangest rule in quantum mechanics. Second, observation changes reality. When scientists try to observe the electrons, they suddenly fix themselves in a single location, proving that reality depends on measurement. Third, this rule may not only apply to electrons but could extend to the entire universe. Scientists believe that it is possible that the entire universe was also in superposition until someone observed it for the first time. Does this prove that our reality depends on an observer? This experiment has various applications. Quantum computers are superfast. Utilizing superposition, quantum cryptography enables ultra-secure data transfer. In the future, work is being done on the possibility of quantum teleportation. When the electron was not observed, it passed through multiple paths simultaneously, meaning it was in superposition. But as soon as scientists attempted to measure it, it fixed itself in one place. This means that when we do not observe, particles exist in multiple locations at once. Thinking phase, now it's your turn. Electric light bulb, if you were in superposition, where would you want to be at the same time? Electric light bulb, do you think we will understand this concept better in the future? Electric light bulb, does our reality truly depend on our ability to measure it? Write down pointing backhand index, share your thoughts in the comments. Smiling face with smiling guys. This thought experiment was proposed to explain an important concept in quantum mechanics, superposition. Schrödinger conceived this experiment to illustrate how the rules of quantum mechanics differ drastically from our everyday reality. In this experiment, a cat is placed inside a closed box along with a radioactive substance, a Geiger counter, and a vial of poison. If the radioactive substance decays, the Geiger counter detects it and releases the poison, killing the cat. If the substance does not decay, the cat remains alive. However, according to quantum mechanics, until we open the box, the cat is in a state of superposition, meaning it is both alive and dead at the same time. The moment we open the box, we see that the cat is either alive or dead, but before that, it existed in both states simultaneously. This can be understood using the example of flipping a coin. Until the coin lands, it exists in both heads and tails possibilities, but once it lands, we see a definite result. Schrödinger's experiment highlights the difference between classical and quantum physics. In classical physics, an object cannot exist in two different states simultaneously, whereas in the quantum world, particles can exist in multiple states at once until they are measured. This concept plays a crucial role in technologies like quantum computing, quantum cryptography, and understanding the origin of the universe. Quantum computers differ from classical computers because they can exist in both 0 and 1 states simultaneously, allowing for exponentially faster computations. Quantum cryptography enables secure communication, as any attempt to intercept a quantum message would instantly alter it. Scientists also believe that superposition played a role in the origin of the universe. Until the Big Bang occurred, everything remained in a state of uncertainty. Schrödinger's cat experiment demonstrates how our reality can be influenced by quantum-level uncertainty, and this concept is helping scientists develop many future technologies. String theory is one of the most complex and mysterious concepts in physics, also known as the theory of everything. This theory attempts to explain that all the fundamental forces of the universe, gravity, electromagnetism, strong and weak nuclear forces, and all fundamental particles, quarks, electrons, photons, etc., operate under a single theory. According to string theory, the smallest components of our universe are not point-like particles but extremely tiny, vibrating strings that create different particles by vibrating in different ways. Just as different strings of a guitar produce different sounds, the vibrations of strings determine the properties of particles, mass, charge, spin. This means that if electrons, quarks, and other particles are actually tiny strings, their type will be determined based on how they vibrate. The greatest feature of string theory is that it attempts to unify quantum mechanics and the theory of relativity, general relativity, into a single framework. Einstein's theory of relativity works on a large scale. Gravity, the universe, planets, and celestial bodies, while quantum mechanics operates on a microscopic scale. However, these two theories do not align with each other, meaning, when we try to understand extreme conditions such as black holes or the Big Bang, the mathematical equations of both theories fail. String theory attempts to merge these two into a single unified theory. The world we live in consists of three spatial dimensions: length, width, height, and one time dimension, referred to as 4D spacetime. However, string theory suggests that the universe actually has a total of 11 dimensions. These extra dimensions are so small, compactified, that we cannot see them. According to calculations, string theory's equations do not work without these dimensions. These are known as Kaluja-Klein dimensions. It is possible that these dimensions exist all around us, but our brains are only adapted to perceive 3D space. This means that we are like an ant walking on a 2D sheet of paper, unable to perceive the 3D world, even though it exists. If string theory is proven correct, it could help solve many mysteries. It could aid in understanding black holes and the Big Bang. It may reveal the secrets of dark matter and dark energy. It could provide a way to unify gravity and quantum mechanics. It could also strengthen the concept of the multiverse. Scientists consider it the theory of everything, but more experiments are needed to validate it. Perhaps in the near future, when science and technology advance further, we will be able to test this theory. Until then, it remains one of the most exciting puzzles in physics. Turbulence, turbulent flow, is a condition in which a fluid, liquid or gas, flows in a chaotic and disordered manner. It is one of the most complex puzzles in science, often referred to as the last unsolved mystery of physics. Even Einstein was unable to fully understand it. Turbulence is a type of flow that involves disorder, uncertainty, and rapidly changing rotations, eddies. When a fluid or gas flows slowly, it is called laminar flow, smooth flow. However, when the flow becomes fast and starts moving chaotically, it is called turbulent flow. In turbulence, the fluid or gas breaks into many small eddies and vortices, making its direction and speed unpredictable. When water flows slowly through a pipe, it moves in straight streams, laminar flow. But when the tap is fully opened, the water currents become disorganized, creating turbulence. Understanding turbulence is difficult because it is mathematically extremely complex. Creating an accurate mathematical model of turbulence is challenging, as it is influenced by a large number of uncertainties and small-scale energy streams. It is completely unpredictable and irregular, which cannot be explained by the normal laws of Newtonian physics. Energy spreads across both small and large scales, making it difficult to measure and control. That is why physicists and mathematicians call it the hardest problem in fluid dynamics. Force that acts on an object without touching it is called non-contact force. Gravitational force pulls everything toward the Earth. Magnetic force works when a magnet pulls an iron piece without touching it. Electrostatic force can be observed when a comb, rubbed on dry hair, lifts small paper pieces. A magnet attracts iron but not wood, because magnetic force only works on magnetic materials. Raindrops fall from the sky due to gravitational force pulling them down. Now, grandfather said, force not only moves objects but also changes their direction and speed. If no force is applied to an object, it will either remain stationary or move at a constant speed. If a bicycle is not pedaled, it remains still. But if someone pushes it, it starts moving. Force changes the speed or direction of an object. When Arav kicks a football, it flies in a new direction. For every action, there is an equal and opposite reaction. When Arav jumps off a boat, the boat moves backward. Now Arav understood everything. He happily said, "So force drives the world. Gravity makes things fall, friction prevents us from slipping, magnetic force attracts metals, and action-reaction launches rockets into space." Grandfather smiled and nodded. "Yes, son, Force is the mysterious power that keeps the universe in motion. Thinking face what would happen if Earth's gravitational force suddenly disappeared. Thinking face can force be seen, or can only its effects be felt? In the mysterious world of science, particles hold a special place because they are the tiny building blocks of our entire universe. Asterisk when we break an object into smaller and smaller pieces, we eventually get atoms. Asterisk but if we break atoms further, we find even smaller particles called fundamental particles. Asterisk these particles make up everything in the universe: you, me, Earth, stars, air, water, everything. If a building is made of bricks, then the building blocks of the universe are these particles. Scientists have discovered many particles, but the most important ones fall into two main categories. 1. Particles that create matter. 2. Particles that generate forces. Matter-forming particles are called fermions, which build everything in the universe. They are divided into two groups: quarks and leptons. Asterisk quarks are the smallest particles that form protons and neutrons. Asterisk quarks never exist alone, but always group in threes to form protons and neutrons. Asterisk there are 6 types of quarks: up, down, top, bottom, strange, and charm. Pushpin example. Asterisk a proton consists of 2 up quarks and 1 down quark. Asterisk a neutron consists of 2 down quarks and 1 up quark. Leptons are light particles, the most famous of which is the electron, which orbits around the nucleus of an atom. There are a total of 6 types of leptons: electron, muon, tau, electron neutrino, muon neutrino, and tau neutrino. For example, the electron is an essential part of an atom, while the neutrino is a mysterious particle that is extremely light and can pass through anything without interacting. The second type of particles are those that generate forces, known as bosons. These particles create fundamental forces that keep matter together. They are also called force carriers. The 4 major bosons are photon, gluon, W and Z bosons, and Higgs boson. Asterisk photon is responsible for light and electromagnetic force. Asterisk gluon holds protons and neutrons together to form the atomic nucleus. Asterisk W and Z bosons are responsible for the weak nuclear force, which controls radioactive decay. Asterisk Higgs boson, also known as the God particle, provides mass to particles. Without it, everything would be floating in space. Most of these particles cannot be seen directly, but scientists detect them in laboratories. In Switzerland, there is a massive research facility called the Large Hadron Collider, LHC, where these particles are studied. In 2012, the Higgs boson was discovered here, which was considered a major breakthrough in science. These particles play a crucial role in the universe. Asterisk quarks and electrons combine to form atoms. Asterisk atoms make up all elements. Asterisk elements form Earth, stars, planets, galaxies, and everything around us. So, these tiny fundamental particles are the building blocks of our entire world. Asterisk fermions are matter-forming particles, including quarks and electrons. Asterisk bosons are force-carrying particles that hold the universe together. Asterisk the most famous particles include white heavy checkmark protons and neutrons, made of quarks. White heavy checkmark electrons, orbiting around the nucleus of atoms. White heavy checkmark photons, particles of light. White heavy checkmark Higgs boson, which gives mass to particles. So, next time you look in the mirror, remember you are also made of these tiny, invisible particles. The mysterious world of particles, understanding through a unique story. Milky Way. Once upon a time, in a small village, there lived a curious boy named Arav. He always wanted to understand everything in depth. One day, he went to his grandmother and asked, "Grandma, if we keep breaking things into smaller and smaller pieces, will they eventually disappear?" His grandmother smiled and said, "Not at all, my dear. Everything has something inside it. Let's understand this with an experiment." She took a clay laddu and broke it in half. Then, she broke that piece in half again. And again. And kept breaking it into smaller pieces. Now tell me, Arav, if we keep breaking it like this, what will remain? Arav thought for a moment and said, very tiny particles will be left. Absolutely right. Grandma said, everything is made up of tiny particles, called particles. These particles are so small that we can't even see them. Grandma then pointed towards a beautiful temple and said, look at this grand temple. But what is it made of? Bricks. Arav replied instantly. Exactly. Just like this temple is made of bricks, the entire universe is made of tiny building blocks, these tiny particles. Arav's eyes lit up in wonder. Oh, that means I am also made of these tiny particles. Yes, my dear. Grandma laughed. We all, and everything in this world, are made up of these tiny particles. Grandma continued, these tiny particles are of two types, fermions, which form matter, and bosons, which hold things together. Then, Grandma began her story. A long time ago, when the universe was born, tiny particles called fermions were floating in space. They were alone and scattered everywhere. Then one day, another type of particle, called bosons, arrived and said, we will help you stick together. And just like that, fermions and bosons came together to create the entire universe. Arav laughed. Oh, so fermions are like bricks, and bosons are like cement. Exactly right. Grandma nodded. Now Arav understood that the world is made of particles, but he was still curious. Grandma, what are these particles? Grandma smiled and replied, quarks, the tiniest particles that make up protons and neutrons. Electrons, which orbit around the nucleus of an atom. Photons, which give us light. Higgs boson, which gives things their weight. Now Grandma asked Arav, if you shrink down and enter inside an atom, what will you see? Arav imagined, I will see protons and neutrons at the center of the atom, and electrons revolving around them, and somewhere, photons shining. Absolutely right. Grandma said, now think when you see sunlight, it's actually photons reaching your eyes. Arav was thrilled. Oh, so even light is made of tiny particles. Yes, my dear. Arav thought for a moment and asked, if everything is made of these tiny particles, does that mean we are just a collection of particles too? Grandma replied, absolutely right. We are all made of very tiny particles, and they are what drive us and this entire world. Now Arav completely understood that nothing is possible without particles. We are all made of these tiny particles. This universe is the most magical wonder of science. Particles are the true building blocks of our world. Small blue diamond fermions which create matter, quarks and electrons. Small blue diamond bosons which provide forces, photons, gluons, Higgs boson. Small blue diamond most important particles, white heavy checkmark protons and neutrons made of quarks. White heavy checkmark electrons, which orbit around the nucleus of an atom. White heavy checkmark photons, which give light. White heavy checkmark Higgs boson, which gives mass to things. Now, whenever you look at anything, remember it is all made of tiny particles. If you liked this story, show your love. Heavy black heart. White heavy checkmark like if you found this video informative and interesting. Public address loudspeaker share so more people can learn about this amazing mystery. Bell subscribe for more such unique and knowledge-filled stories. Your likes and comments inspire us to create even better content. Smiling face with smiling guys, so tell us, did you find this story fascinating? Comment below and share your thoughts.